Hey guys, this is the nuclear chemistry review, which I go over the worksheet I gave in class on Friday. You should also check the email because there should be attached a digital copy of this review sheet in case you didn't take it home with you, because I've noticed in the classroom there are a bunch of unanswered copies flying around the classroom, which means some of you didn't take it home with you. Just saying. Anyway, let's start with number 1. What is nuclear chemistry about? It's the study of changes that occur in the nucleus of atoms. So let me write nucleus in here. Please forgive any noises in the background. I'm watching Stranger Things Season 2. If there are any Stranger Things fans out there, just know that Season 2 just came out over the weekend. And here I am just kind of getting a late start today on episode 3 right now. Alright, let's continue. Number 2, a nucleus is unstable when there are more blank than protons. Neutrons. Just remember that inside the nucleus you have both neutrons and protons. So it's all about whether or not the ratio between protons and neutrons leads to more neutrons or more protons. An example of that would be carbon. So two common isotopes for carbon, let me just make some little notes here. C12 and C14. So this means you have 6 protons and 6 neutrons, whereas this one here, 6 protons of course because it's still carbon, but also 8 neutrons. Carbon-14 is more unstable because here you have much more neutrons than protons, whereas carbon-12 is more common, it's more stable, even ratio between protons and neutrons. Okay. Now number 3. What are the 4 modes of decay? Which of them are particles? So there are 4 of them. There's alpha, beta, gamma, and positron. I'm going to put some symbols here. Alpha looks like A, beta looks like B, positron is like a positive electron, and then there's gamma, which looks like an upside down fish, or like Y. Okay. Beta particles are negative, alpha particles are positive. Okay. Now, which of these are particles? It's these guys, alpha, beta, and positron. Gamma, on the other hand, is radiation. Now, we're going to rank these 4 in terms of mass and penetration strength. Let's start with mass. So we're going to rank them in terms of least to greatest. So the smallest mass here is gamma. It's not even a particle, it's just radiation energy. Gamma has the least mass. Then you have beta and positron being equal masses. They're like almost the same, just opposite in charge. And then you have alpha particles being the greatest. Now let's talk about penetration strength. So penetration strength meaning how strong can it go through objects and obstacles. So least to greatest, alpha being the biggest has the lowest penetration strength. So a lot of it's inversely related to mass. So the bigger they are, the lower the penetration strength. Beta and positron again are equal to each other because they're equal size. And you have gamma being the strongest. Because it's just radiation energy, it's able to go through many obstacles and substances. It's the greatest, it's the strongest, highly penetrating. Okay. So let's make a note here for some relationships. Mass goes up, penetration strength goes down. To show that these are inversely related. Okay, where do you find these decay modes of radioactive isotopes? Remember there are 2 tables we dealt with, table N and table O. Table N is the first one we deal with. And then where do you find the types of decay modes? This here is table O. Now we move on to the next topic of half-life. Does half-life measure time or mass? Half-life measures time. Time required for radioisotope to decay in half. Where do you find the half-life? Radioisotope. So this here is table N as well. Number 9, what happens to the radioactive isotope after a half-life passes? So this goes back again to number 7. What happens? Radioisotope cuts in half. So an example of that is a 100-gram sample breaks down into 50 grams. All right, number 10. What does artificial transmutation involve? So remember natural versus artificial. Artificial is man-made, it's forced, it's non-spontaneous because it means you can't find it in nature. It means you need energy to start it. And it also requires particles to bombard them. You guys hear that music? It's background music for the episode. It requires particles to bombard isotopes to start reaction. So it's not like natural transmutation where you have one single radioisotope decaying. It's where you have a radioisotope and another particle colliding with each other, jump-starting this transmutation process. So artificial means you need to assist it. You need to assist it with another particle to jump-start it. It's non-spontaneous. You need to force it. Whereas natural transmutation is more spontaneous. You don't have to force it because it occurs in nature on its own. Alright, number 11. What are the differences between natural and artificial mutation? Oh, I kind of jump started into this. So let's do natural here. Now let's do artificial here. Alright, so you have one reactant. Here you have two reactants, which means you have two on the left side of the equation. So you have the radioisotope plus the particle. Here it's just the radioisotope. So this one's spontaneous, this one's non-spontaneous. Okay. Artificial transmutation has two types of reactions. We have fission and fusion. So let's talk about fission here, fusion here, and then whatever's common between them. Commonalities. Okay, so fission is breaking large radioisotope into two elements. Whereas fusion is two elements into one larger element. Now this fusion reaction, it's hard to do. Now why is that? So when you're putting two elements together, you're essentially fusing two nuclei together. And the nuclei, you have one positive nucleus and another positive nucleus. When two positives try to come together, they want to repel each other. They want to go away from each other. So that's why it's hard to do. You need a lot of energy to bring these two nuclei together. And because you have two like charges, they want to repel, likes repel, so they want to push away from each other. All right, now back to fusion. Let's use the nuclear bonds. And then fusion reactions are pretty much power of the sun. Commonalities essentially convert mass into energy, and it's a lot of energy. And then now the last question here is dangers and benefits of using radioactive isotopes. So dangers here on the left side and benefits on the left side. Let's talk about them. All right. Dangers. Let's use blue. Radioactive waste. Radiation that's harmful. It's also nuclear weapons. It leads to nuclear weapons. Benefits, high energy output. Also, you have some medicinal benefits. So that's with the use of short half-life radioisotopes. Because the shorter it is, the quicker they disappear. So it's out of your body in pretty much a short period of time. And then for dating, so an example would be carbon dating of substances. So you can use carbon radioactive isotopes to help you determine the age of some substances. That's why it's called like dating. How far back did they go? And usually those you require the use of longer half-life radioisotopes, just so they can last longer. Okay. And now practice questions 1 and 2. Write the nuclear equations for the decay of phosphorus 32 and radium-226. So that requires us to use the periodic table. I'm sorry, not the periodic table, the reference table, table N and table O. So let's start with phosphorus. Alright, phosphorus 32 I'm going to highlight in blue. So phosphorus 32, you look it up, the symbol is there. Phosphorus is also element number 15, I believe. And it undergoes beta decay. So you are writing the symbol for beta. So betas are -1. They have a mass of 0 and a charge here of -1. So you will have to look this up on table O. You copy this symbol directly from table O and you put it in your nuclear equation. Now when figuring out what is the missing part of our equation, you need to consider that we need to conserve both mass, which is the top number up here, the mass numbers, and the charge or the atomic numbers down here. So if it's 15 on the left side, we need to have 15 total on this right side. So let's figure that out. Alright, so our top number is 32 total on the left, and so we need to have 32 total on the right. So seeing how there's a 0 already there, we can just easily put 32 up here. So notice how our sum is still 32 on the left and 32 total on the right. Now we need 15 total on the left and right side. So 15 on the left, 15 on the right. So we already have a -1. What would add with -1 to still get 15? Let me show you. It's going to be 16. Now why did I pick 16? Look here, 16 and a -1 together, you add them up and you get a total of 15. So make sure these two things stay the same. So that means we got to look up element number 16, and that would be sulfur. And that's how you write the nuclear equation for decay of phosphorus 32. Now you apply the same idea to radium-226. Okay, so radium-226, so Ra 226 on top. We need to figure out what's the atomic number of radium. So after checking the periodic table, radium has an atomic number of 88. Alright. So we also have to go back to table N to figure out what's the decay mode of radium-226. Oopsies. It decays by alpha particles, alpha decay mode. So alpha particle has a symbol. You need to check table O for the other details. So there's a 4 up here and a 2 down here. So it's almost the equivalent of a helium atom. So that's why you'll sometimes see helium He 4 and 2 on the top and bottom. So it's just alpha particles are essentially the same as helium atoms. Alright, now we gotta fill in the rest of this. Remember, keep in mind, we need to keep 226 as our total on the top number. So if we already have 4 on the right side, that means we got to fill in the rest to add up to 226. So 222 will be our top number. And on our bottom number, we need a total of 88. We already have 2 there. So that means we need 86. To finish us off, we need to look at the periodic table to find out what element number 86 is. And you should get that radon is our answer. Alright, so that's some practice on writing nuclear equations. I hope that was helpful. Now we move on to the last question on half-life. Here we have a 100-gram sample of technetium-99 decaying over the period of 3 half-lives. How much total time has passed and how much of the sample remains? So let's start with part A. How much time has passed? So technetium-99, you need to look up that, as well as 3 half-lives. So first we start looking at table N to find out what's the half-life of technetium-99. Technetium-99 has a half-life of 2.13 times 10 to the 5th years. That's a lot of years. That's like 21,300 years. Alright, so that's 1 half-life. How much would 3 half-lives be? 3 half-lives. You take that number, multiply it by 3. So 2.13 times 10 to the 5th years times 3. If 1 half-life is that many years, we multiply by 3 for the total number of years. And you should get 6.39 times 10 to the 5th years. That's 63,900 years. Okay, that's part A. Now part B, how much of the sample remains? So we have 3 half-life periods. We start out with a 100-gram sample. So 1 half-life passes, I like to denote it with arrows. 1 half-life passes, we have 50 grams. That's 1 half-life. Another half-life, you cut it in half again, 25 grams, that's 2. And 1 more half-life, that's 12.5 grams. So notice how after 1 half-life passes, you cut your sample in half, another one passes, you keep cutting it in half. So 3 half-lives leaves from 100 to 50 to 25 to finally 12.5 grams. So that's our answer for part B, 12.5 grams. And this is the end of our nuclear chemistry review video. I hope this was helpful. Again, if you lost a copy of it, you could download a digital copy right on the email attached to this. And good luck, guys. I know this is an optional quiz, but it still doesn't hurt to take it if it's either going to help your grade or not.